Chapter 16, Acid-Base Equilibria. Let's start off by looking at some properties of acids and bases that you may be already familiar with. Acids tend to have a sour taste. An indicator, litmus paper, tends to turn red when it comes in contact with acids. And if you put a metal such as magnesium in, let's say, hydrochloric acid, it'll produce quite a bit of hydrogen gas. Bases, on the other hand, tend to taste bitter. They feel slippery, like in a lot of soaps and cleaners. They tend to turn litmus paper, which again is an indicator, blue. And another really common indicator, phenolphthalein, it'll turn phenolphthalein pink in titrations. We're going to stick with just really investigating the Bronsted-Lowry acid-base definition. Now, the Bronsted-Lowry acid-base really focuses on following where the proton, which is an ion that just contains is an H plus ion, a bare proton, just kind of following where that goes in an acid-base reaction. When there's an abundance of H plus ions in water, it tends to bond with the water and produce H3O plus, which is known as the hydronium ion. Now, the Bronsted-Lowry theory emphasizes where this proton goes. And so you can see right here, the Bronsted-Lowry acid in this picture actually is transferring a proton to the Bronsted-Lowry base. And then since this is an equilibrium reaction, we have the products on the right-hand side, but we also see we have what we call a conjugate acid here with a proton and a conjugate base. And we'll talk about what a conjugate acid-base pair is here in a little bit. So Bronsted-Lowry acid is a substance that donates a proton to another substance in an acid-base reaction. A Bronsted-Lowry base is the substance that can accept a proton in an acid-base reaction. Seems pretty simple. We have a proton donor, we have a proton acceptor. However, there are sometimes substances that can behave as both a Bronsted-Lowry acid or a Bronsted-Lowry base, depending on what they're combined with or what they're reacting with. A really good example is water, and I'll show you an example where water behaves as an acid and when where it actually behaves as a base. So in this first example, you can see we're dissolving hydrogen chloride gas in water. And what's happening is the hydrogen chloride is then donating a proton or its H plus to water, and we're forming hydronium. In that case, water is acting as a Bronsted-Lowry base because it's accepting the proton from the hydrogen chloride. Now, in the next example, we see that water is actually behaving as the Bronsted-Lowry acid because it's donating a proton to ammonia, which is NH3. And so we're forming ammonium, polyatomic ion, and hydroxide. And so literally what's happening is water is donating that proton to the ammonium, and we're actually increasing the hydroxide concentration in that solution. So in this case, water's acting as a proton donor or a Bronsted-Lowry acid. Therefore, water is what we call amphiprotic or sometimes called amphoteric, depending on the textbook. And that just means it's capable of behaving as both a proton donor and a proton acceptor. Conjugate acid-base pairs. Often you'll see this HX and X minus. Now, HX is your acid and X minus is your base. Or in one hand, we have our proton donor in the HX, and we have X minus, which is going to be our proton acceptor. One is a reactant, the other one is a product. So let's take a look at what we mean by that. What you'll notice is the conjugate acid-base pair differ by only an H plus. So the only difference between this acid and this base is the H plus that is connecting the two of them. There are always two sets of conjugate pairs in any Bronsted-Lowry reaction. So for example, if we take a look at the example below, we can see we have nitrous acid, which is HNO2, and we can see in this reaction that it is donating the proton to water, which in this turn is behaving as a proton acceptor, and it is forming a conjugate base and a conjugate acid. So one of the things you'll notice, and this is so hard to do with these notes, but what you'll notice is that the Bronsted-Lowry acid is donating a proton to the water. Therefore, after it donates that proton, it forms something that then can accept a proton. And so its anion or its complementary pair is called a conjugate base. Now, water, on the other hand, is behaving as a Bronsted-Lowry base because it accepts the proton. And on the other side of the reaction, it now is capable of donating the proton, so it becomes the conjugate acid. This takes a little bit of practice, so you can do some on your problem set, and we'll do a few examples here in a second. I want to show you one more because I think this is a really good picture. In this case, water is behaving as a Bronsted-Lowry acid, and it's donating its proton to ammonia, which, since ammonia is accepting the proton, it is called the Bronsted-Lowry base. On the other side, or on the product side, we see the hydroxide ion, which is the conjugate base for water. So again, we have water, which is a Bronsted-Lowry acid, and the conjugate base pair is the hydroxide ion. And then ammonia, which is behaving as the Bronsted-Lowry base, accepts the proton and now has a conjugate acid pair on the other side, or on the product side. And that ammonium ion is capable, if the reaction reverses, of being the proton donor. So one of the things that you'll notice is that every Bronsted-Lowry acid has a conjugate base on the product side. Reactant side, product side. Every Bronsted-Lowry base has a conjugate acid pair on the product side. Reactant, Bronsted-Lowry, base, product, conjugate acid. So take a moment, pause the video, see if you can write the formula for the conjugate acid of each of the following. Okay, did you come up with this? H2SO3, HF, HPO4 2-, and HCO3+. One of the things you'll notice is that the conjugate acid, and the only difference between the conjugate acid and its Bronsted-Lowry base pair is one proton. And every time you add a proton, you take away a negative charge. In the case of carbon monoxide, adding a proton actually gave it a positive charge. Not all acids and bases are equally good at donating or accepting protons. This is a really good time to go back and take a look at your strong acids and your strong bases. The stronger the acid, the weaker its conjugate base. The stronger a base, the weaker its conjugate acid. For example, somewhere in Google Classroom, you all have a table that looks really similar to this. And you'll notice at the top of this, here are some of the strong acids that we had talked about earlier in the year. Well, what you'll notice is their conjugate bases, which are right across from them. The conjugate base, again, differs by just an H plus ion. And what you'll notice is they have negligible basicity, which means they are very, very weak bases. In fact, they're so weak that they really don't have any tendency to want to really take a proton back. And if you think about it, by definition, a strong acid is basically something that donates a proton and really does not want that proton back. So hopefully it makes sense that its conjugate base pair would not really behave as a good proton acceptor. Now we have this whole area in the middle with weak acids and weak bases. And what I want you to notice is that there are a lot more weak acids and weak bases than there are strong acids, and down here at the bottom, strong bases. We have a few very strong bases down here, which are really good at accepting protons. And if you take a look at these, if this accepts a proton, we get hydroxide, which is what increases the base. If this accepts a proton, we have hydrogen gas, which is a very stable compound. If CH3 accepts a proton, we have methane. So these become really strong bases because they're excellent at accepting protons. But the compounds or ions that they form really have no tendency to want to donate that proton back. And so that's part of the definition of being a strong base, and completely having the ability to just accept that proton and not want to give it back. The conjugate bases of weak acids are weak bases. So all of this area in the middle that we were talking about with weak acids and basically donating that proton, the weak base that accepts that proton, they do it, but they're not really that good at it. So if we look at acetic acid, which is right here, CH3COOH, and its conjugate base, which is the acetate ion, it's both a very, the acetate ion is not very good at accepting protons, and acetic acid is not really that great at donating protons. All of these weak acids in the middle are the acids and weak bases that we see that have a lot of reactions where the arrows go in both directions. So we'll spend some time playing around with that and looking at Kas and Kbs because, I know how much you love equilibrium. And so all of these weak acids and weak bases end up having reactions that are going to have an equilibrium expression. So in every acid-base reaction, equilibrium is going to favor the transfer of the proton from the stronger acid to the stronger base. Because of this, it's going to form a weaker acid and a weaker base. Example, hydrochloric acid, which we know is a really strong acid. When we dissolve that in water, we put that in water, the hydrochloric acid completely disassociates. Water grabs onto that proton, leaving behind chloride ions. Since hydrochloric acid is a really strong acid, and if we go back and take a look at our strong acid, strong base, we can see that water is a stronger base than the chloride ion. So what we would expect is the equilibrium would lie far to the right, or our equilibrium constant would be much larger than 1. And that's why we see the arrow go in just one direction. We see the strong acid reacting with the stronger base, producing a weaker conjugate acid and a negligible conjugate base. Here's another one. The acetic acid, which is a CH3COOH, is reacting with water. Now, one of the things we'll notice is we have a double arrow here, and that tells you something. That tells you that you have a weak acid, a weak base, and on the other side, we have a weak base here, the CH3COO, which is the acetate ion, is also not very strong, and hydronium H3O plus is not a strong acid. So now it's kind of a battle of which one's the stronger base. Is acetate the stronger base, or is water the stronger base? Well, if we go back and take a look, we can see water right here. And let's see, here it is. Here's water right here. And we can see when it comes to bases, water is not a very strong base. And here's acetate, which is a much stronger base compared to water. And so what we see happen here is, since acetate is a stronger base than water, and hydronium is a stronger acid than acetic acid, then this equilibrium lies to the left. And we would expect our equilibrium expression to favor the reactants in this case. Aha, double arrow. There we go. All right, So try this. For each reaction, predict whether the equilibrium lies to the left or to the right. I left the acid base strength diagram up here. Take a couple minutes, see if you can figure it out, and then we'll post the answers and go from there. So hopefully you realized with this one right here that the HPO4 2 minus is way down here when it comes to acids, and the H2PO4 is right here when it comes to acids. So H2PO4 is slightly stronger acid than the HPO4 2 minus. Because of that, I would say that this reaction lies or favors the left. So probably having a double arrow here would be a better idea than an arrow just going in one direction. I'll have to fix that later. But we would say this reaction most likely lies to the left. Now we can double check that with water. If we look at the bases, let's see, we see OH way down here, which is a fairly strong base. Oops. Pretend like I didn't post that. And then we see water, which is up here. So again, we see OH is the stronger base. So the stronger acid and the stronger base are going to force this reaction to the left. Okay, and then you already saw ammonia, which is NH4, and OH. So NH4 is our proton donor. We can see the conjugate base here. We can see OH. Let's see, NH4 plus is right here when it comes to acids. NH3, I don't even see on here. Where is it? Don't see it anywhere. So we would say NH4 is going to be a stronger acid than NH3, since I don't even see it on here. And if we take a look at OH, OH is a really pretty strong base. And again, water is way up here. So this is going to have our stronger acid and our stronger base on the left. So again, then we have our conjugate base, which with the NH3, and the water is going to be our conjugate acid. So this one would definitely favor the product, since our stronger acid and stronger base are on the left, on the reactant side. Okay, I think that's it. Let's see if that helps. I'm going to spend some time tomorrow working on some problem sets and some extra problems. Sorry this is so rough, but you know, it's the best I could do. So hopefully this helps, and we'll talk to you soon. Bye.